Hey guys, and welcome back. So before we dive into any Houdini stuff, I wanted to go over the fluid workflow and explain all the steps that we have to go through from start all the way to be able to render the flip fluid data. And we have two options on how we can start or create the source for the flip fluids. We either have, let's say, a pool of water, for example, where we want to have a car crash into it, or a lake where we want to have, again, a spaceship rise from it or something like that. In that case, in these two scenarios, we have a predefined set of water that we're going to use. Okay. In the case of flooding, for example, where we have a stream of water pouring in, or a river, or anything that has continuous emission, we use a different type of emitter in that case. And with the lake or a pool or anything where we know the quantity of the water that we need, we're going to use something called flip tank, where we basically take a specific domain, a bounding box, and fill a certain amount, as much as we need, with points, and use those to emit from. Now the flip fluid is going to use that in the first frame and emit that much fluids, and then we're going to use that for the remaining of the sim. In the case of continuous emission, we're going to take, let's say, for example, we have a character running and we need to emit water from that character, for example. We're going to convert it into a certain type of data and then fill that character with points, and those points will be fed into the flip fluid solver, where we emit every frame new fluids. If we have, for example, a river, we're going to use a certain geometry that we use to emit fluid continuously. If we have a waterfall, for example, or anything where we need to emit fluid, in that case we're going to use a geometry and feed the points every frame into the solver. And then once we have these two things, we're going to feed points to the flip fluids. That's the main idea. We're going to feed it points, and then it's going to use those points and move them to mimic the water behavior. Now, as we all know, water is incompressible, so it doesn't lose volume and it doesn't add volume. And solving the incompressibility feature or the pressure equation cannot be done through points, because points are just spares. And to solve anything that is basically a fluid-like behavior, where we need to keep the pressure consistent in a certain domain, we're going to use voxels for that. So we're going to need to run a smoke sim, similar to an explosion, for example. We're going to create internally, or the flip fluid, the flip solver internally creates this, and that's what it uses to solve the pressure equation. Now the points is what we see and what we use to convert into a mesh. So basically what happens is we feed our points, the flip fluid is going to run the smoke sim internally to solve the pressure, decides how much velocity there is, and pushes the voxels in the right direction, and then takes a set of points and advect them through that volume. And the idea with flip fluids is that we need nicely distributed points at any point in time, and this is where the flip fluid does its magic. Basically give us a nicely distributed set of points that we can convert into a mesh later. Now we feed in the points into the flip fluids. We feed in any extra forces we have, if we have winds or anything like that, and any collision geometry, whether it's static or animated. And then it goes through the smoke sim, the points advection, which is a particle sim basically. So we have a smoke and a pop sim, and then we import back a set of points and something called an SDF, a surface field. And this is what has been used inside the smoke solver. This data is going to be useful for us in various different ways, and we will understand the usage for this data later on. Now we import the points from the flip fluids solver. We need to convert those points into a geometry. To do this, we first need to convert them into a volume, a VDB data, and then from that VDB we convert it back we convert it into a geometry, and this will give us the final renderable mesh of our sim. And then from all of this, we're also going to use the SDF primarily to create a whitewater source. So this new node in Houdini 17, they have improved it, and it now uses volumes to create the source. Previously it was done through points, and so this node is going to analyze the input, and based on, let's say, the curvature, the turbulence, the vorticity of the sim, and depth of the sim, it's going to analyze and decide where it's going to emit from, where it makes sense to place the foam as a source. And then once we have the whitewater source, we're going to feed that into the whitewater solver, which will start emitting points, which is a particle sim basically, and then we need to feed it the same collision geometry. So if you have rocks or ground or anything, everything has to go through this. And if we need to add any extra things to the whitewater solver, or if we need to add forces and stuff like that, we're going to also do that here. The output from this is points, and we can either render this as points or decide to convert them into a volume and render them as volume. So you can choose to either render the foam as points again, or as an actual volume. And these are the two things that we're going to render from the overall sim. Now, each of these steps has different different ways to create forces, create collisions, create sourcing. There is various ways on how we can do geometry generation, which is a very tricky problem. There's many ways on how we can tweak the whitewater solver, as well as how we can add forces to the whitewater solver. There's ways how we can create an efficient or a more intelligent volume representation of the whitewater if we decided that that's how we're going to render it. There's so many options. Each of these steps has so many things that we can work on. There's so many problems that we need to fix, and as we go through these different projects, we're going to cover certain things. And the first one we're going to start with in week 2 is the rock splash, which will give us an extensive overview of the flip fluid workflow and various advanced techniques. Now for this week, we're going to go over this workflow without the whitewater. We're going to take a look at the flip tank technique and emitting from a geometry, or and basically emitting every frame fluids. And then at the end, we're going to take a look at the whitewater workflow briefly, and what kind of data we need to cache, and everything that is required to properly do all the steps needed to create a whitewater sim. Now the reason for this is we want you guys to get comfortable, or very comfortable I should say, with the flip fluid workflow. This also includes any wedges that we need to run, adding the overlays on top of the OpenGL render using the dailies and the wedge setup that we've provided, and also trying to push the quality of the sim as much as you can. It's very important to get comfortable and understand that, and to understand the limits of the hardware that you have access to. There's no limits as to how much you can push the quality. If you have 16 gigabytes of memory, you need to see how much points or how much data you can fit into that. If you have 32, you need to hit the limit. If you have 64, and so on and so forth. Sim time can vary anywhere between 4 to 50 hours. It really depends on how complex the setup is and how much details you want to create from the sim. And understanding and knowing these things is very, very important. From week 1, we want you guys to fully understand the production ready workflow, be able to create sims, and know exactly how much time it's going to take to create a high-res sim, a mid-res sim, and a low-res sim. And let's start taking a look at the flip fluid workflow in Houdini. Thank you guys for watching, and see you in a bit.